Thank you, Matthias, for giving me the opportunity to talk today on the result of a European project funded by the European Union we've been working on in the past 3 years. So this is a team from Fraunhofer ITWM, including myself and Heiko Andre, Darek Niziela, and Inga and Konrad. Most of you or some of you will know already. And let me first introduce our department shortly to you. For those of you who don't know us yet, we are a department of the Fraunhofer ITWM, the Fraunhofer Institute for Industrial Mathematics, located in Kaiserslautern. The department is called Flow and Material Simulation. And what we do projects in all kinds of fields, where we also develop software. Some of you might know these software tools or some of the software tools. For example, fluid foam grain for all kinds of fluid simulations. BEST, which is also integrated in GeoDict, and also FieldMath, which is a tool for mechanical simulation on microstructures, which is integrated in the ELASTODICT module of GeoDict as well. And the ALMA project, as I mentioned, is a project funded by the European Union. It's ended just a few days ago. There were 9 partners involved from 4 different countries. Maybe it was a rather industrial consortium. So the main OEM involved in this project was Ford. So the idea was to convert the vehicle structure of a internal combustion engine to battery electric vehicle and reduce the weight and environmental impact of the structure with using advanced materials. There was advanced steels, various advanced steels provided by ArcelorMittal, and special kind of fiber reinforced composites, SMC, provided by a Spanish company or Basque company called BATS. And our contribution was the modeling and the simulation of these SMC materials for crash prediction, including both the process simulation and the mechanical simulation. And one of the interesting parts of this project was that it was really on industrial level. So in the end, we had to do validation of the new vehicle structure at TRL8. So like in real production environment. And it was very interesting and exciting for us to bring our methods into such an environment. What is SMC? I don't know whether you know this guy. Is actually it's a kind of fiber reinforced material, which is produced by compression molding. So here you see on this slide, you see some of the presses which are used to produce the parts made out of SMC. And you also see a picture where the operator puts these SMC prepregs into the machine, and then it is compressed and brought into the final form. And what are the advantages? Of course, we used it in ALMA to reduce the weight, so the low density compared to steel is the main advantage in this case. It is also rather cheap. It is easy to produce, and it has rather good mechanical properties due to the fiber reinforcements. And then, which is another advantage of SMC, you can add different filler and additives for different purposes, for example, for flame protection and so on. But of course, at the same time, it's not an easy material to model. Of course, the mechanical behavior depends on the fiber alignment of the fiber, on the fiber orientation, the volume content, and also on the stress state. And another big challenge is, of course, the recycling, which was also tackled in this project, but not by us. There was the Dutch research organization TNO, which did also some very interesting work on this topic. But I will not cover this in my talk. I will focus on our contribution on the simulation chain, which we built up for the characterization of SMC. So what is maybe special, what is special about SMC is that the fibers are very long and they are aligned in bundles. So many of you have probably, you know, the case of injection molded materials where we can resolve the single fibers on the microstructure level and then obtain by methods of homogenization also the macroscopic behavior. Here in the SMC we have an intermediate scale which we have to consider. It's the scale of the fiber bundles where we don't resolve the single fibers anymore but the bundle structure. And then what we can do on these mesoscale models, we can perform virtual tests. And with these virtual tests, we can calibrate material cards for, here in this case, it was LS-Dyna for simulate, which can be used directly in LS-Dyna. And the reason why we use these material cards is, just as I said, it's a project at TRL8, so it should be integrable into existing workflows at Ford at the full vehicle simulation. And therefore, we have to use these predefined material behaviors. Yeah, but it was also interesting to use GeoDict and field mask for such a purpose to obtain material cards which can then be directly used in LS-Dyna. And the process simulation at the same time provides the fiber orientation which are needed for to characterize the anisotropy of the fibers in the final component. Let me quickly speak about the process simulation model which we implemented in Fluid. The unique feature of Fluid in this respect is that the matrix material, the resin, can partially overflow the fibers, so they can flow at different speeds. And therefore, in the equations to be solved, there's an additional term depending on a parameter alpha, which describes the fiber-fiber and fiber-fluid interaction. And yeah, depending on the choice of these parameters, this controls the speed difference between the flow of the fibers and the resin. And then, of course, what we need then is also a permeability tensor, and this was one of the first purposes where we used GeoDict for in this project, was to estimate the permeability tensor, which depends on the fiber orientation and the fiber volume fraction. And this is the first parameter, or the first study we did then in GeoDict on structures generated with FiberGeo. We generated structures with given orientation and volume fraction, calculated permeability, and then deduce formulas for the permeability as a function of fiber orientation and fiber volume fraction. And what you see here on the left of the slide is, in the beginning we started with structures where the fibers were resolved, but then it turns out that the permeability within the fibers is very low, and the main flow is always between the bundles. Therefore, we use structures where the fiber bundles are modeled as solid, and thereby we could reduce the simulation time a lot. Otherwise, it's actually not really be possible to perform such a study. Then we did some validation by CT scans. CT scans in this respect is a bit a difficult task because the fibers are so long and the bundles are so large, and still you need to resolve their structure somehow by the CT scan. So usually the CT scans are too small to really give a good impression of the fiber orientation. What we did is we averaged a larger number of CT scans to obtain some meaningful values and performed 3 different positions over the plate and compared this to the fiber orientation we obtained from fluid. And as you see from these numbers, for example, at P1, at the position where the initial blank was positioned, the agreement is quite well. P2, the agreement is actually not very good in the center of the plate, but at the same time, the variations between the CT scans is also very large. And at the rightmost position, P3, we have a slight alignment of the fibers in flow direction, both in the CT scans and in fluid. So this is by far from being exact, but at least it gives us some validation of the process simulation results. And finally, we did a validation for a realistic geometry, where we did a filling study, where we had a filling study performed by Butts and compared it to the flow font obtained with fluid. And actually, we saw that we could predict the flow front with good accuracy, as you see here on the pictures. Let me continue now with the mechanical characterization. As we saw in the CT scans and also from the process simulation in these plates, we have a slight fiber alignment, and our colleagues at the Leibniz Institute for Verbundwerkstoffe, they performed some tensile measurements for us at quasi-static strain rates to characterize the anisotropy of the mechanical behavior. And we obtained actually, there is some anisotropy. The Young's modulus is rather different between the 0 degree and the 90 degree direction. Also, the ultimate tensile strength is quite different between the 0 degree and the 90 degree direction. But you see also from these measurements that the variations between different samples can be very large. So how to model this? As I said, we wanted to obtain a material card in LS-Dyna, which can reproduce this behavior using a 3-scale modeling approach. And another point where we put a lot of effort in is to keep the experimental effort as low as possible. So we start on the micro scale inside the fiber bundles, where we assume isotropic nonlinear material behavior for the resin, which can be characterized by DMTA measurements. And for the fibers, we assume linear elastic behavior, and then we obtain a material model for the fiber bundles by homogenization. In this material model of the fiber bundles can then be used in mesoscale simulations, where the fiber bundles are the resolved objects as before. We generate representative volume elements, perform virtual tests on this mesoscale, and from these virtual tests we derive macroscopic stiffness tensors and anisotropic hardening curves, exactly the data we need as input for an LS-Dyna material card. And this material card then can be used directly without any additional parameters. It gets all the data needed from the mesoscale simulation and can be directly used in LS-Dyna for simulations on the component scale. For the fiber bundles, as you might know, in field mass, in Elastotech currently, we have the possibility to use anisotropic elastic material laws or isotropic plastic material laws. And with anisotropic elastic material laws, we can, of course, model the anisotropy of the composite in the elastic regime, but in the nonlinear regime, the agreement is much worse. And with the isotropic plastic material law for the fiber bundles, we have acceptable agreement in the nonlinear regime, but the stiffness anisotropy is not correctly predicted. So at the moment for this project, we decided to use the isotropic plastic approximation for the fiber bundles. But we are currently working on an anisotropic plastic model, which implemented as a user-defined material function, which could then also be used in ElastoDict LD. But for the moment, we stick with the isotropic plastic model. So for those of you not familiar with LS-Dyna, as I was also not very familiar with the software before, when we started the project, it was still called LS-Dyna. Now it's part of the ANSYS software. We chose a material law, Math2Market, which is quite common for fiber reinforced composites, which is a combination of an anisotropic elastic and anisotropic plastic material model. So as input for this material card, you need an anisotropic stiffness tensor, you need a plastic hardening curve, and then you need Langford parameters or Hill parameters, depending on the element type which you use in your finite element simulation. And luckily, all these simulations you can obtain from these mesoscale simulations. What you need to do is you need to generate your fiber bundle geometry, and where you can prescribe a specific orientation tensor. You can perform linear elastic simulations to obtain anisotropic stiffness tensors. You can perform tensile tests in 0, 45, and 90 degrees. And from those, you can directly get your plastic hardening curves and the Langford parameters. And then you can perform these kind of calibrations for each orientation class which you want to consider in your component. This could also be done for injection molded materials. Then you would not have this mesoscale model as a structure, but then you would just have the regular structure where the fibers are resolved. And actually there's even an advantage compared to experimental characterization, because in these kind of virtual experiments, you know exactly the fiber orientation which you used for your calibration experiment, which is not the case if you extract samples from plates or components. You can never be sure which orientation you are actually testing. And in this case, with virtual structures, this you know exactly because you know it exactly because you prescribe it. And then, now I come finally to the results, because I see my time is running out as well. We can actually model the anisotropy, or we can reproduce the anisotropy seen in the tensile tests. Here in these pictures, the dotted lines are the measurements and the solid lines are two simulations. The blue line is an isotropic model in LS-Dyna, and the red curve is an anisotropic, is the simulation with the anisotropic material card which we have calibrated. Let's say there's of course room for improvement, and that's why we are also still working on the nonlinear anisotropic material function for the bundles, but the agreement is actually it's good. It's of course so initially in the project we started with this blue line with the isotropic card, and you see that it's a large improvement to use the anisotropic material law instead. But as I said, in this project, we don't want to stop here at tensile tests. We want to go to the component scale. And another complication which appeared in the course of the project was that BUDS decided to add textile reinforcement to the SMC. So let me skip a bit the details. We built new mesoscale models. We obtained new material cards. We also added failure criteria and damage model in LS-Dyna, and this is now validation experiment performed by our project partners, and you see here on the left the experiment and on the right the simulation in LS-Dyna with our material card. And I think you will agree that the prediction of the simulation is actually really accurate. So we have the failure at the screws, but there's no failure in the middle where the impactor is, and this is perfectly predicted also by the LS-Dyna simulation. So this allowed then Ford in the project to use our material card in the virtual validation of the crash behavior of a new structure which was developed in the project. And we could provide an important input for the whole project chain. And the project, so here's just a summary slide of this 3-scale modeling approach we did from the microscale to the mesoscale, and finally to the component scale. And here's also a slide on the main results obtained in ALMA with the help also, I mean, of course, there was a lot of work involved, not only from us, but also our material card helped in providing the crash safety of this new vehicle structure, which resulted in a 22% weight reduction of the vehicle structure, reduction in the CO2 emissions, and since it is for an electric vehicle, this translates into a 6% increase in range, given the same, using the same battery size. And I think the project was a big success. We were very happy to be part of it. I think we could contribute well in this very, very, very applied environment. Yeah, here on this picture, you might see the 2 arrows going from buds to the structural parts. These are actually the components where our material card was then used in the final vehicle structure. So yeah, that's it. I hope you like my talk. I'm happy to try to answer your questions.